Welcome to this lecture on the geometric intuition behind eigenvectors. Today, we'll explore two fundamental questions. Why are eigenvectors indifferent to transformations? And how does an eigenbasis differ from the standard basis?
Let's start with a fundamental question. What does the word eigen actually mean? The word eigen comes from German, meaning characteristic, own, or inherent. Before we dive into eigenvectors, let's review linear transformations. A linear transformation takes vectors as input and outputs new vectors. It preserves vector addition and scalar multiplication. Most importantly, it can be represented by matrix multiplication.
Let's begin with understanding why eigenvectors are indifferent to transformations. Let us start with a coordinate plane. We will apply a linear transformation to various vectors and observe what happens. Here are three arbitrary vectors in our space. These vectors point in various directions. Let us apply this transformation matrix A. This matrix will rotate and stretch our vectors. Watch carefully what happens when we apply the transformation. Notice how these vectors not only change their length, but also rotate to new directions. Their arrows point in completely different directions after transformation. But now, let us look at something special. These are eigenvectors of our transformation matrix. The red vector points in the direction of one eigenvector, and the green vector points in the direction of another. I've drawn dashed lines to show the entire span of these eigenvector directions. Now watch what happens when we apply the same transformation to these eigenvectors. This is the key insight. The eigenvectors only get stretched or compressed, but they stay on the exact same line. The red eigenvector gets stretched by a factor of 3, and the green one stays the same length. But crucially, neither one rotates to a new direction. To see why this happens numerically, let's look at the math. When we multiply a standard vector like 1, 0 by our matrix, the coordinates get mixed, resulting in a new direction. But look what happens with the eigenvector 1, 1. The result is 3, 3, which is exactly 3 times the original vector. The ratio between x and y stays identical. Mathematically, we express this as a times the eigenvector equals lambda times the eigenvector. For the red eigenvector, lambda equals 3, meaning it triples in length. For the green eigenvector, lambda equals 1, so it stays the same length. Here is the key takeaway. Eigenvectors are indifferent to the transformation in the sense that their direction remains unchanged. The transformation only affects their magnitude, scaling them by the eigenvalue. This is what makes eigenvectors so special and useful in linear algebra. Why does this matter? Because eigenvectors reveal the fundamental axes along which a transformation acts purely as a scaling operation. They show us the invariant directions of the transformation. Now let's explore how an eigenbasis differs from the standard basis, and why this difference is so powerful. Let us compare two different coordinate systems. On the left, we have the standard basis. The standard basis consists of I hat pointing along the x-axis and j hat pointing along the y-axis. These are the familiar unit vectors we all know. Any vector in this space can be expressed as a combination of these basis vectors. For example, this yellow vector equals 2 times I hat plus 1 times j hat. We can see it broken down into its horizontal and vertical components. Now, on the right side, we have the eigenbasis. This basis is formed by the eigenvectors of our transformation. The eigenbasis vectors point along the eigenvector directions. Notice they're not perpendicular to the coordinate axes. They are rotated at 45 degrees. These dashed lines show the eigenaxes. The same yellow vector can also be expressed in the eigenbasis. Now it equals 1.5 times E1 plus 0.5 times E2. The components are different, but it's the exact same vector in space. Here's where it gets really interesting. Let's see what happens when we apply our transformation in both coordinate systems. In the standard basis, our transformation matrix looks complicated, with off-diagonal entries. But in the eigenbasis, the matrix becomes diagonal. The diagonal entries are simply the eigenvalues. This diagonal form is the key difference. In the eigenbasis, the transformation is just scaling along each axis. No mixing between coordinates. No rotation. Just pure scaling. Let us summarize the key differences between the standard basis and the eigenbasis. The standard basis is aligned with coordinate axes and works for all transformations. But the transformation matrix can be complex with off-diagonal entries. Under transformation, vectors generally change direction. The eigenbasis is aligned with the eigenvector directions, and it's specific to each transformation. The magic is that the transformation matrix becomes diagonal, and the basis vectors only scale without rotating.